a little bit how to sort 5-element array. Our goal, we want to use 7 comparisons. Our goal. Okay? Yeah. Then the first round preparation. So we use the tournament method. Tournament. Yeah. The first 3 comparisons. Here, the typical tournament method. Yeah. Oh, let me turn off the light. Yeah. The first 3 comparisons. After that, we get the relationship like that. Yeah. So we make some reasonable assumptions. Yeah. So in the diagram, X1 largest. So we have a longest chain, order the chain, longest, A1, A3, A4. Yeah. Then second order the chain, A1, A2, shorter. Yeah. When now we consider next comparison number 4, we compare X5 and X3. Yeah. Here, based on our experience, why we do comparison like this? Yeah. X3 is in the middle of the longest ordered chain. Yeah. This kind of comparison, we get experience from binary search. Yeah. So I believe all of you know the binary search. Although our next part, we will study binary search. But before that, you know how to do the binary search. So we use that experience. Yeah. X5 compare it with X3. Yeah. In this way, we can, because we know binary search is very fast. Yeah. So based on that, we hope this way we can get a better performance. Yeah. But this comparison would give us 2 cases. And these 2 cases are not symmetric. Okay? So we have to discuss each one by one. Yeah. If it's symmetric, we only need to discuss one of the 2 cases, but not symmetric. Yeah. So the symmetric means if you put a mirror there, you flip, yeah, basically the same thing. But here, because there is this branch, right? This branch, it won't be symmetric. Okay, yeah. So we need to discuss the first case and the second case. Yeah. So this is the first case, case number 1, and the case number 2. Second case. All right, Grant, remind me, check your attendance after the class. Yeah. All right, now, case number 1. For case number 1, all right, let's continue. Let's look at our comparison number 5. Can anyone tell me what do you want to do for comparison number 5?
X5 and X2 for case 1.
X5, yeah. So you have many options. Yeah. The correct one should be X5 and X1. X5 and X1. Yeah. Why? Because if you do one comparison between X5 and X1, you will get 4 elements in order: X1, X5, X3, X4. Just after one comparison. No matter it's greater than X1 or less than X1, you extend your longest ordered chain, right? You extend your longest ordered chain. And its length becomes 4, okay? from 3 to grow it to 4. Yeah. So that's why here our comparison number 5, comparison number 5, x1 and x5. Okay. Yeah. After that, there are two cases, right? Yeah. The first case, x5 is greater than x1. Second case, x5 is less than x1. But although you can discuss these two cases, but here, let's try to minimize the number of cases using this thinking. How to minimize? Which one would be worse? Yeah, because we are targeting the worst case, right? These two cases, one of the two cases is worse than the other. We want to select the worst one. Do you think x5 is larger than x1, it's worse, or x5 is less than x1, it's worse?
X5 larger than x1.
Why? You need to, yeah. You need to give me some good reason, Justin. Can you see which case is worse? Here, we want to, worse means it forces us to do more work. That means it's worse. Which one would give us more work to do?
Talking about the entire diagram or
entire diagram? Yeah.
okay.
Yeah. Visual understanding. You look at the diagram. When you put x5 higher than x1 would be worse. x5 lower than x1 would be worse. Yeah. Because we know x5 is above x3. So you don't worry about that. Okay.
If x5 is lower than x1, then we have to compare it to x2.
Yes.
Wouldn't that be the worst?
That's correct. That's correct. The worst case would be x1 higher than x5 next, then x3, x4, and x2. Yeah, let me explain to other students. Yeah, why x5 lower than x1 would force us to do more work. Because look at this branch. x2 is below x1, right? But if you put x5 lower than x1, then it forces you to do more work because you need to consider the relationship between x2 and the other three elements. If you put x5 higher than x1, then x5 is out of the consideration. You only need to consider the relationship between x2 and the lowest two elements, right? So you need to do less work, okay? Here, this case, this one, you need to do more work because you need to compare x2 with these three elements. 3 versus 2. So 3, you need to do more work, right? 2, you need to do less work. Yeah. So that's the reason we target the worst one. All right. So for this case, now at this point, we used 5 comparisons. 2 more to go. Remember, the goal is 7 comparisons. 2 more comparisons, we should put all elements in place. 2 more to go. Do you think after 2 comparisons, we can put x2 in place? Another binary search, right? Another binary, because you compare x2 and x3. Compare the one in the middle, okay?
Yes.
It's higher, lower, 1 more comparison.
Yes.
Yeah? All right, so after that, yeah, so here, number 6, number 7, we put all in place, okay? All elements in place. So here I do not specify, yeah. From the diagram, you know how to do the last two comparisons, yeah. The binary search, okay? Yeah. So here you can see by the binary search way, binary search idea, okay? So here you can see it's very important using the binary search idea when you do comparisons, okay? What is the best way, fastest way to do comparisons? So when you have an ordered chain, yeah, so the binary search is the best way to do the comparisons, okay? Yeah. All right, so that's the first case. Second case, similar. Second case, after one comparison, x4 and x5, x4 and x5, yeah, we get the longest ordered chain, x1, x3. Now x4 higher, x5 higher, symmetric, right? This time symmetric, so we just pick one of the two. Yeah, we don't need to consider both. This time we can use symmetry for x5, symmetry. And x2 here, then binaries, oh, keep, yeah, I'll get out of my presentation. Yeah, I need to change the color. All right. Yeah. So another binary search situation, right? Two more. Another binary search situation. So number 6, number 7. Binary search. Type comparison. Okay? Binary search type comparison. All in place. Then we're done. Okay? We cover all the cases, especially the worst case. Yeah. So using this way, yeah, from this example, so you can see when we solve questions like this, you can use the diagram way, yeah. Because in this way you do not need to write a lot of words, okay, a lot of explanations. Yeah, yeah. Because when you do this, I can understand your idea, okay? From the diagram, I can understand. So your comparison, 1, 2, 3, 4, 5, you know. Yeah. Although you can write a lot of words, yeah, but usually a little slower, right? Because you need to organize your language, okay? Yeah. In this way, yeah. Just represent your idea. Diagram way, yeah. All right, yeah. So we we solved this problem. Yeah. So this one very challenging. Yeah. But after here we use our background insertion sort binary search. We use these two background knowledge we learned, yeah, so we can solve this problem. Yeah. All right, yeah. So let me move to part B. Binary search. All right. It's very important, although most of you know the binary search, but we have through this topic so we can learn some problem-solving methods. Yeah. All right, B.1, binary search elimination. We want to use the elimination method to understand the binary search. All right, yeah, I need to connect my remote control. All right. Yeah. Given an ordered array and a search key V. Question, how to find an index I such that V equals A of I? So that's the search problem. Yeah. But an important property in our data, ordered array. So we can take advantage of this property to help us reduce the number of comparisons. Yeah. Yeah. All right. Yeah. Analysis idea, reduce the problem size by the ordered data property. Yeah. So here we use the idea we used before, problem size reduction. Problem size reduction. We know when we reduce the problem size, then most of the time we can do better. Yeah, here I use most of the time because we can find special cases. In some special problems, in special cases, when the problem size smaller, the difficulty actually greater. Yeah, that exception could happen. Yeah. Here I do not go too far, but just give you idea a little bit. That is, when you do prime factorization, you know, sometimes the number n becomes smaller, the factorization is harder. You may have that experience. For example, when the number n equals 1,000, the prime factorization very easy, right? 1,000. Prime factorization is so easy, right? 2 cubed times 5 cubed. Yeah, prime factorization. But when n becomes smaller, 347, the number is smaller than 1,000, right? But the prime factorization is harder, right? If you do prime factorization on 347, you need to do more work, right? Then n equals 1,000. So this special example tells you sometimes the size is smaller, but the difficulty of the problem is higher. It could happen, right? But in general, here we talk about in general. In general, when the problem size becomes smaller and the problem, difficulty of the problem will be easier. Here, our binary search, we try to make use of that property, this property. Now, reduce the problem size. All right. Yeah. By elimination method. Yeah. When we do elimination, because we can make a good prediction. After we make good prediction, we can apply the elimination method. Yeah. Let me explain this analysis details. All right. How can we take advantage of the ordered data property, by prediction? Okay? Yeah, by prediction. All right. Explore the order property. Yeah. So look at this diagram. The given array, it's an ordered array. Now there is a search key. V is the search key. Yeah. All right. When we do our first comparison, we have many options. Yeah. We can compare V with the last element, with the first element, with any element in between. Yeah. We have so many options. Yeah. Which one do you think is the best choice? The one in the middle, right? The boundary search tells us, but why the one in the middle is the best? Yeah. Now we want to understand this step. Although you have some intuition, to feel if you compare V with the one in the middle, you will get the best overall result. Yeah. 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 For the worst case, here we consider the worst case, okay? Not the best case. Okay, so here we consider the worst case. All right, yeah, yeah. All right, yeah. In all these options, let's see for the worst case. What is the largest possible portion of data that could be eliminated after one comparison? So here we use the elimination method. We want to eliminate, after one comparison, we want to eliminate as many elements as possible. As many elements as possible after one comparison. Then that comparison would be the best from the elimination point of view to tell us which one is the best. Yeah. So our goal, we want to eliminate the maximum number of elements after one comparison. Yeah. But when you do that, you need to consider the worst case, not the best case. Okay? All right. Yeah. So after how many elements can be eliminated? We have so many different cases. All right. Yeah. Look at the first case. Yeah, we want to do experiments a little bit. Yeah. The first experiment we want to do, we want to compare V with the last element. That's our first experiment. Then we have two cases, right? One is V greater. Yeah. So if V equals A sub A minus 1, then it's the best case, right? Yeah. So we don't worry about that. So here we consider worst case. So V, the first case, V is greater than A sub N minus 1. Second case, V is smaller than A sub N minus 1. All right. Two cases. Which one is worse? Easy to see, right? V less than A sub N minus 1. That's worse, right? And this one better, right? This case better. This case worse, right? Better and worse. And we should look at the worst case, right? Yeah, the worst one. The worst one, how many elements can be eliminated? If we look at the worst case, after first comparison, how many elements can be eliminated? Only one. Yeah, that's too little, right? That means this option is not good. Okay, this option is not good. Yeah. Then next you will see if we compare, if we compare V with the element in the middle, then it's bad. It will be better. Yeah. So here, another way of understanding is Murphy's law. Okay, Murphy's law. Yeah, because Murphy's law tells us anything that can go wrong will go wrong. That actually tell us we should focus on the worst case, right? That could go wrong. That's the worst case, right? and will go wrong. So that means we should target the worst case. Okay, here. Yeah. All right. Yeah. So we compare the one right in the middle. If we do this comparison, then you also have two cases, right? Left subcase and a right subcase. So this one, if you make this comparison, you have left subcase, and then you also have right subcase, right? Which one is worse? You compare one in the middle. Almost the same, right? Yeah. Almost, yeah. Here, yeah. Let's treat these two cases are the same. Yeah. The number of elements that could be eliminated the same. If you go to the left branch or if you go to the right branch, you can eliminate approximately 1/2 of the elements, right? 1/2 of the total elements, approximately. Yeah. Then the two subcases would give you same number of elements to be eliminated, right? Yeah, that understanding. Okay, yeah, but that's the maximum number of elements you can eliminate, right? Because if you move this point to the left or to the right, any direction, one of the two branches would be smaller, right? Yeah, but the elimination would be that smaller one, right? So if you do not choose the midpoint, you would do worse because the number of elements to be eliminated would be fewer, right? Fewer. Because, after data distribution is not even, okay? Yeah, not even. Murphy's law tells you need to focus on the worst one, right? Yeah. So the better one, the smaller branch would be eliminated. Not the larger branch would be eliminated. Smaller branch would be eliminated. Yeah. But this way, midpoint, the two branches are the same. No smaller branch, no larger branch. So either one. If you do the elimination, you get the same result. Same performance. Yeah. So that's the idea of the, binary search. This explains the main idea of the binary search. Why we compare given search key to the element in the middle, or we call it median, the median element. Yeah. Yeah. All right, so here. All right. Yeah. But at this point, I also want to give you another interesting idea when we do problem solving. Yeah. When we do problem solving. Yeah. Here, I bring up this Murphy's law to help you understand why we want to focus on the worst case. Okay? Murphy's law. Okay? But there is another interesting idea also addressing this point. So why and how? Yeah. This second view tells us how to focus on the worst case. How? Okay? Yeah. So also very interesting. Yeah. Here, let me mention that idea called adversary argument. Adversary argument. Argument. What's that? Adversary. Okay. So here, we imagine we have a smart adversary. Yeah. So our adversary is very smart. Yeah. The role of this adversary, it would force us to do more work. That's the adversary's work, right? When you have an adversary will always try very hard to force you, try to beat you, right? Try to beat you, to force you to do more work. Yeah, yeah. A smart adversary won't give you, easy job to do, right? All right. So now when we do comparisons, we have many options, right? Yeah, we have so many options. But our goal, we want to pick the worst option. We don't want to pick the best option. Yeah. So when I did a grading of the middle, many students give me the best case, not the worst case. Okay. So from now on, we should target, when we do problem solving, we should target the worst case. Okay. Never try to get the best case. Always target the worst case. Yeah. When you target the worst case, yeah, this idea, adversary argument, you imagine there is some adversary playing against you. Yeah. So how to use this argument? When you have multiple options, many options, which one to pick? You ask your adversary, which one you would like to give to me? Yeah. You ask your adversary to give you. Yeah. A smart adversary would give you the worst case. Okay? Yeah. A smart adversary would always give you the worst case, not the best case. Yeah, it's not a strong adversary, right? Give you, not the worst case, it won't be a strong adversary. Okay? Yeah. So a strong adversary always gives you the worst case. Yeah. So in this situation, we have two branches to go, right? When we do comparison. Okay? Two branches. One larger branch, one shorter branch. Which one you should select? You ask your adversary. Which branch you would like me to go? Okay? Yeah. So your adversary will tell you, go the larger branch. Because when you go that direction, larger branch, you can eliminate shorter branch. Yeah. You eliminate fewer number of elements. Yeah. So that's another thinking. Another thinking you can use in problem solving. Okay? Yeah. So adversary argument. Yeah. Later in our discussion, yeah, if I find the similar situation, I will use this adversary argument. Okay? To help us to understand the situation better, yeah, to make the right decision targeting the worst case. Yeah. All right. Yeah. Yeah. So let's continue. Yeah. All right. Yeah. 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 Another way. So here I said, the balancing principle, strategy. Yeah. So that's another view. So we have many different views. We can. Yeah. So here, erase another view to understand the problem, the balancing principle. This view also very useful. That means when we have chance to distribute our data, here we compare the point in the middle. That middle point split the data into two halves, right? Yeah, that's the way to distribute the data. So here the balancing principle tells us when you have chance to split your data, you should choose the most balanced way to split the data. Okay? Then you will get the best solution. Yeah. If you split the data evenly, yeah, then you will get the best solution. That's the balancing principle. Okay? Yeah. Yeah. So when you have chance to make your decisions, distributing the data, the evenly distributed data usually corresponds to the best performance. Okay? The binary search, we want to get the best performance for the worst case. Yeah. Here, sometimes students got confused. Yeah. We want to get the best algorithm, right? Nobody wants to get a worse algorithm. Okay? So our goal, we always want to find the best algorithm. But the best algorithm targeting the worst case. So here, you see the words best, worst. Don't get confused. Okay? You see one word best, another word worst. But don't get confused, these two words. Okay? Yeah. So let me say it again. In our algorithm design, we want to find the best algorithm targeting the worst case. That's our goal. Okay? That's our goal. Yeah. So you see this best word and the worst word, but sometimes some students confused. We want to find the best algorithm, but those students misunderstood. We want to find an algorithm targeting the best case. They use the best in that way, best case. Yeah? Yeah, it's wrong. So we want to find the best algorithm targeting the worst case. Okay? Yeah. So do not get confused. Yeah. Yeah. Because sometimes argue, you say we want to find the best algorithm, then we should target the best case. Because the best case, we can get best algorithm. Is it correct? No, it's not correct. Yeah. The best algorithm means the fastest possible algorithm targeting the worst case. Fastest. Targeting the worst case, it's fastest. Yeah. We all compare the worst case. Okay? Yeah. We always, when we test several different algorithms, we always target the worst case. And we want to pick the one with the best performance. Yeah. Later, we will have a homework assignment. In our homework assignment number 2, we will have that one. Okay? We will have several different algorithms, and those algorithms targeting the worst case. But the number of comparisons is different. You should pick the smallest number of comparisons because that's the best algorithm, right? But some students, they pick the largest number because you said the worst case. So they pick the largest comparison number. Then that's the worst algorithm. That's not the best algorithm, right? Try to understand that point. Understand that point. When you have 3 algorithms, they have different number of comparisons. But those 3 algorithms all target the worst case. All target the worst case, okay? Yeah. But you should pick, when you make the final decision, you should pick the one with the smallest comparison number. Okay? Yeah. Yeah. So homework assignment, we will have that question. Yeah. Do not get confused. Yeah. All right. Yeah. Yeah. Right. So B.2, efficiency analysis of binary search. Now, because after B.1, we know how to implement binary search. Yeah, we know. So the next step, we want to do the analysis, efficiency analysis. How many comparisons do we need for the binary search? Best case, worst case, average case. 3 cases. Best case, easy. Best case, 1 comparison. Okay? You're very lucky. When you make your first comparison, you'll find the element corresponding to your search key. You're done. That's best case. Yeah. Then, worst case, average case. Much harder. Yeah. All right, so let's look at diagram for the binary search. Number of comparisons for the worst case. So let's do some analysis. How to get the number of comparisons for the worst case. Yeah. Let me look at how much time I left. Yeah. All right. Let me use this line segment representing the total number of elements in an ordered array. Now, so the length of this array corresponds to the data size. When we do binary search, every time we drop 1/2 of the data size, right? After each comparison, we can drop 1/2 of the data size. Yeah, so we keep doing this. Yeah. So let me use a diagram to show this process. Yeah. After the first comparison, yeah, in the middle, yeah, then we drop one of the two subarrays because we assume they have almost the same size, yeah, evenly distributed, almost the same size. We just drop one of the two subarrays. Then the remaining data, we need to do the second comparison. Somewhere another midpoint comparison at the midpoint. Then we drop another subarray of the half of the current data size. Okay, current data size. Drop. Okay, another half. Next, we keep dropping, but after k comparisons, the data remaining corresponds to a small line segment, right? Yeah. So the data size, the data to be considered, its size becomes smaller and smaller. Yeah. So let's look at the relationship. The number of comparisons and the data size numbers. Okay? What's the relationship? Yeah, here. One comparison, half of the original size. After two comparison, quarter of the original data size. And after k comparison, the data size becomes n over 2 to the k. Yeah. All right. Yeah. That's the, data size relationship. Yeah. All right. The next question is, what is the last comparison? If we do split like this, you cannot split forever, right? You have to stop somewhere. Yeah? So we need to identify the point where we have to stop. What is that termination point? We need to find that termination point. Okay? We have to terminate. Yeah. So we need to identify that point. Yeah. Yeah. To do that, you need to find the condition. Yeah. On the worst situation, you do not need to do split. Yeah. It does not make sense to do further split. You need to catch that point. That is, think about, if the remaining data only contains one element, do you need to do? No. Yeah, because only one element. You have no choice. What you can do, just the last comparison, compare with this final survival element, final one. Yeah. You do not need to do further split. You cannot split one element, right? Yeah. Yeah. So the last split should correspond to one element remaining. Yeah. Only one element remains. Yeah, based on that understanding, we can find an inequality to describe the condition for after the last split. After, yeah, you have last split. After that, then you have a condition that tells you no further split needed. Yeah, let's look at that condition. Yeah. After the last comparison, you know the data size, right? You know the data size. Think about if the data size is strictly less than 1, then that line segment cannot cover more than 1 element, right? It can only cover at the most 1 element. Yeah, because the data size number, this is the data size number. Okay, this number strictly less than 1, that means it can only cover at the most 1 element. No further split. All right. Yeah. So in that way, so the data size should be strictly less than 1, but its previous data size should be greater or equal to 1. It's previous. It's previous. Okay. Yeah. N over 2 to the k minus 1. The previous one should be greater or equal to 1. Then you can do another split, right? Yeah. Because it's greater or equal to 1, it can cover at least the 2 elements, right? So you have another chance to do a split. Okay? Yeah. So that is the condition, describing the termination point. Yeah. All right. So let us do some form change on this inequality by removing the common denominator. So we have this inequality. Yeah. Because our goal, we want to find the range for k. The range for little k. K corresponds to number of comparisons for the worst case. Last split, that's the worst case. Yeah. Number of comparisons for the worst case. Yeah. All right. Then we take log base 2. Yeah. So we have this inequality. Okay, log base 2. Yeah. Less than or equal, but this side strictly less. That difference is important. Okay, that difference is important. Yeah, we need to consider that little difference. Yeah. All right. Next, we can write the range for the k. Right. Yeah. So here we assume n is known. Yeah. Yeah. The range for k. Yeah. So let's look at the range. Yeah. So for the worst case, we have this inequality. So what is the range for k? We want to derive the worst case formula. Worst case formula. Yeah. Then this inequality, by algebra, we can get an equivalent inequality. So this is equivalent inequality. Okay, so that's the range for k. So you get a lower bound log base 2 of n, that's the lower bound of k, and the upper bound 1 plus log base 2 of n, upper bound. Okay, yeah. All right, so now, yeah, because after we get this inequality, we are not quite satisfied. We're not quite satisfied with this one. Why? Because we know k is an integer. K, number of comparisons, k must be an integer. But log base 2 of n, not necessarily integer, right? Log base of 2 could be, non-integer number. Okay? Yeah. So that means log base 2 of n, it's not an integer expression. It is not an integer expression. Okay? Yeah. In order to improve this inequality, can we convert that non-integer expression to integer expression? Because k is an integer, we should use integer expression to describe k, right? Why use a non-integer expression to describe integer k? Okay, that means you can improve. You can improve your estimate. Yeah. So next step, we want to convert non-integer expression to integer expressions. Yeah. So when you do that, non-integer expression, you take a floor function, ceiling function, right? Remember? So when we do, the easiest conversion, either floor function or ceiling function. Okay? Yeah. All right. From the upper bound, we should take floor function, right? Going down. Upper bound, going down. Okay? Lower bound, we should take ceiling function, moving up, right? Approaching up. Okay? Going down. Yeah. We squeeze, right? From two sides, we move approach to K to describe K more precisely. That's the idea. Okay? Yeah. So the upper bound, yeah. All right, so here, because the upper bound, there is an equal sign. So when we apply floor function, that's easy. But the lower bound, there is an unequal sign, strictly less than sign. If we move up, then we don't know. Should we take equal sign or unequal sign, right? There is uncertainty. There is uncertainty for the lower bound. So we need to going back to look at our previous inequality. Yeah. We need to go back a little bit because we want to extract more information from our previous inequality. Okay? Yeah. The problem is we want to fix the strictly less than sign. And we want to write a version use less than or equal. We need to contain that equal case. If we contain equal case, then when we use the ceiling function, yeah, then that's easy. Yeah, because the integer one is included. Yeah, when we use the ceiling function. Unequal sign, the ceiling function may not be include that integer, right? So that will be harder. Yeah. So here we want to fix this unequal sign first. Yeah. All right. And strictly less than 2 to the k. Can we tighten this inequality? Improve this inequality a little better? And integer 2 to the k, also integer. These two integer, but the second integer is strictly greater than the first integer. Can you improve slightly? Including the equal case. Equal case. Yeah. If the larger one is reduced by 1, is it still greater or equal to the less one? Reduced by 1. Only by 1. Because we know the larger one is strictly greater than the smaller one. So it is at least 1 more than the greater one, right? Yeah. So if you reduce the larger one by 1, it's still greater or equal. Contains the equal case, right? Yeah. So we minus the larger number by 1. Yeah. Or add 1 to the smaller one. Same thing. So n plus 1 less than or equal to 2 to the k. In this way, we include that equal case. The equal case is included. Yeah. All right. So then we take log base 2. This time, the inequality, both for upper bound, lower bound, we have the equal sign. Okay? We have the equal sign. Yeah. We include the equal case. Then, when we take the floor function, ceiling function, then it's easy. Yeah. Because the integer is included. Yeah. in the lower bound, upper bound. Yeah, integer included. Okay. Yeah. All right. So next, to describe the k, we can use the ceiling function of the lower bound or the floor function of the upper bound. Okay? We have two integer expressions we can use to describe k. Two different integer expressions. All right. Conclusion, two formulas. Those two integer expressions give us two different formulas for the worst case binary search. The first formula, K max, the maximum number of comparisons for the binary search. That's the worst case. K max, the first formula equals the ceiling function of log base 2 of m plus 1. All right. The second formula, the K max equals 1 plus the floor function of log base 2 of n. Yeah. And these two formulas, although with different expressions, but they are the same. Okay? They are the same, but it's hard to see. Yeah. Hard to see they are the same. Why they are the same, right? We can prove these two formulas always the same by mathematical induction. Mathematical induction. Okay? Yeah. Yeah. Here I do not show you the detail of mathematical induction. Okay? Yeah. I want to save some time. I'll just tell you the result. It can be proved the same. And this formula, these two expressions are the same, also given in a textbook in an appendix of our textbook. Yeah. Yeah. So this formula. Okay. Yeah. In appendix. Yeah. All right. Now, after that, this is our worst case formula. Worst case formula. All right? Yeah, worst case formula. From now on, when I ask you the worst case for the binary search, the accurate formula. This is accurate formula. Yeah. Yeah. Before you see this formula, usually when people ask what's the worst case for the binary search, then people write approximate formula. Yeah. So think about if someone asks you what's the worst case, because then people write approximately equal to this number, log base 2 of n. Yeah. Floor function or ceiling function, then they cannot understand. They cannot answer. Is it the floor function of this one or ceiling function of this one? Nobody can answer, right? But precisely after today's class, if you use the ceiling function, you should use this expression. If you want to use the floor function, you need to add plus 1, that expression. Okay? Yeah. Yeah. All right. But most people, yeah. So here, based on this result, here I can tell you this. Here let's target the audience, the computer science people. Yeah, that's our audience. Okay, let's assume that's because we do not target other non-professional, right? What's a what's IT, right? Not IT people, right? If you ask IT people, they may not know the binary search, right? But if we talk about IT people, those people should know the binary search, right? Yeah, computer science people. If you ask any computer science people, what is the worst case number of comparisons for the binary search? You can try if they can give you the correct answer. Yeah, I believe 90% of those people, they cannot give you the correct answer. Yeah, yeah. You IT people, okay? So they work on IT every day. Yeah. So you can try this, okay? If you have a chance, you have friends, okay? You have friends working in IT industry many years. If you have a chance, ask them. Yeah. You know, give a number of elements. N is the number of elements of ordered array to do the binary search. What is the worst case number of comparisons to find an element in the ordered array using the binary search? And ask them if they can give you the correct answer. Okay, you can do, you know, experiment like that. Yeah, because the reason I say this is when I assign homework assignments, many times quiz questions or homework questions I assign. Okay, I give you n. I give you concrete number n. Okay, n equals 1,000. You know, something. I ask you, if we apply the binary search on this array, how many comparisons do we need for the worst case? Yeah. Many times I ask that question. Okay? The wrong answer, I got almost 90%. 90%. When I give quiz questions, okay? Yeah. 90%. Almost 90% couldn't give me one difference. The difference is one, okay? Here, the difference is one. That's one difference, okay? Yeah. So you can see that, yeah. So yeah. Now you have the correct formula. Yeah. All right. All right, yeah. Yeah, so we do not have a lot of time. Let me just say a few more words, because we cannot complete this topic today. Yeah. Let's say what we are going to do next. Yeah. Yeah. Now, the best case we know, 1. The worst case we know, yeah. K-max, we have the formula. Yeah. The next question, what is the average case? Next question we need to answer. We need to we need to know how to calculate the average case efficiency. Yeah, not that easy, right? Not that easy, but we need to know. We need to know how to calculate it. Yeah. So our next topic, we need to calculate the average case efficiency. Yeah. But to do that, before we do that, we will do it in next class. Before we do that, let me ask you the question. Can we calculate the average case efficiency in the simple way, just the best case 1 plus the worst case formula, then the result number divided by 2? Can we use this way to calculate average case efficiency? Simple way? Yeah. The answer is no. Yeah. The answer is no. Why the answer is no? Because if you look at all the cases distributed, it's not in the linear distribution. Okay? Yeah. Yeah. The binary, so later you will see we need to draw a binary tree to cover all the cases. The binary tree, it's like a pyramid, right? The binary tree has many levels. It's like a pyramid. Each level, the number of nodes are different in the binary tree, right? Yeah. When you take an average on all the levels, Each level has different number of nodes. How can you use the linear way to calculate the average? You cannot use the linear way to calculate the average, right? Yeah, so that's the reason. Yeah, you cannot use this simple formula to calculate. Okay? Yeah. All right. But how to calculate? We need to go back to that pyramid and to look at the contribution from each level. Each level, there is a contribution to the average, right? To the final average. Then we need to do a very accurate calculation for the contribution to the final average. Yeah. So we will do it next time. Yeah. All right. Yeah. So let's leave this question next time. Okay. All right. That's it. Yeah.